Welcome to the Machines and Molecules podcast. Machines and Molecules hosts guests from biochemistry, chemistry, and machine learning. And our guest today is Aspuru-Guzik, who is a professor of chemistry and computer science at the University of Toronto. Welcome, Alan.
Thank you, Ikemar. Nice to meet you.
How are you doing today?
Fine. It's a great day here in Toronto. The fall is starting, so it's starting to get a little bit chilly finally.
Yes. Here, the summer is starting, even though it shouldn't, but climate change. Yes. So, Alan, can you tell us a bit about the focus of your work? I saw you've been dabbling into many different areas, among them quantum computing, automatic chemical design, design of chemical fingerprints. Maybe give us a bit of an overview of what has been interesting to you in your research career.
Well, I hope it's not dabbling, but it's actually pushing the frontiers. So what my lab does historically has been thinking about what are the new technological advances in physics and computing science and how they can impact chemistry. So back in 2005, we were basically the first lab that started pushing quantum computing for simulation of molecules and materials. And now it's a big thing. And also quite early on, around 2012, we saw the interesting opportunity, when deep learning started to do well in image recognition. What can it do for molecules and materials? And we were amongst the first groups that were jumping into the deep learning area. Also in 2017, noticing that deep learning was not going to be enough because predicting something requires still making it. We started proposing and pushing the field of self-driving laboratories, which include automation, AI, together with chemistry experimentation to actually make the molecules that we are proposing. So that is kind of the main focus of my lab right now. But if you actually look upstairs, it's actually not dabbling, but it's actually looking at that particular question, which is what are the ways that we can propel molecular discovery based on new technologies.
The idea of an automated lab and molecules that are directly made out of machine designs, I think this is something that many people are fascinated by. Can you tell us a bit about what you found were the big pain points in order to make this dream of automatic molecule design work? Like what are the main technical hurdles in your experience?
Yeah, and we're happy to report it's not a dream, but it's a reality. We just put in the archive a paper, ChemArchive, that was basically the product of 5 years of work. It's 6 labs around the world. There's many authors on this paper, and it required even more than one automated laboratory. It required the integration and connection of several automated laboratories together around the world. So it is hard to make these things happen, but it's possible, and it requires a lot of coordination between different teams and a lot of focus. And so what we are able to do, and then I will get into the pain points. What we're able to do is to actually have a system that looks at the subset of chemical space, something about 170,000 potential molecules, then decides to do reaction optimization conditions, first figuring out how to make the compounds well. That took us about a year. But that led to even a paper on Science just talking about that particular part of the project. And then after that, the next challenge was, okay, let's get the software control of the robots going. Let's get the robots fully integrated with the characterization and the synthesis. And also let's get, once we have these new reaction conditions that took about a year to develop, let's actually start hypercube sampling because we need to have a space to train on. This is a very hard problem that we're trying to solve. It's called the organic laser problem, how to make molecules that emit light to you coherently for new generation displays. So once we were able to have that hypercube sampling, then we were able to do a Bayesian optimization over the subspace of the 170,000 molecules and find a good candidate. So challenges abound. The first challenge is how are you going to have this clunky chemical equipment integrated with software? How are you going to orchestrate it all? How are you going to develop the right machine learning model so that you can learn in the low data regime? That involves a lot of tricks like transfer learning and a lot of featurization that is very important. And then finally, increasing the robustness of the system, because as you build one of the systems, things are going to start happening all the time that are experimental nuisances you have to start fixing until the system actually works. And then as I like to tell my graduate students and postdocs, it doesn't work, it doesn't work, it doesn't work, it doesn't work. When it works, you write a paper, report it, and it doesn't work again. So that's how science is. So now we're moving on to the next challenges of automation and in this space, organic lasers and other spaces. But it's been a great journey, and self-driving labs are around. And I can tell you about several collaborations we have around the world of all the self-driving labs. Industry is interested in them, working on them, and yeah, it's a field. But it's not magic. You have to spend years building a self-driving lab, and then once you turn it on, though, it's like a Ferrari. It just actually does its job very well.
Yeah. So when you say optimization of the reaction conditions, what are we talking about, for example?
So in this particular case, what we're doing is there's a very, perhaps the most popular reaction in pharma, and we use it also for Matthias' discovery in this case. It's called the Suzuki coupling reaction. You take two molecules and then bind them by carbon-carbon bond, which is very useful because then molecules become a little bit like Lego. Then you can just put them together in different ways. The issue with this reaction is that, the best reaction conditions were out there in 2009, done by human experimentation. But once we optimize our two-step one-pot synthesis using yet the old reaction conditions from 2009 and maybe some human tweaks, the yield that we had for our molecules was about, well, it was high, but the yield that we had for our molecules to be detected, which is different than synthesized, it's a long story, but the yield that we have our molecules from synthesis to detector, there's many things under the hood there, was about a quarter. So that means that your machine learning was suggesting molecules, but 75% of them were not makeable by the robot. So what we did is we said, okay, look, if we have these reaction conditions as a starting point, let's create a very diverse set of reactions, a diverse set of reagents, and then optimize and that collective ensemble what is the best collective performance for that particular broad set of molecules. This is work led by Marty Burke and Bartosz Rybaszki, my collaborators. And together with them, we were able to iterate about 4 times with a closed Bayesian optimization loop and find better reaction conditions that in general are better. And also in particular for our problem, they doubled our yield to about 50%, which it's a big difference, right? You waste less reagents, you have more success rate. And also, well, now, machine learning will suggest points that you won't be able to synthesize, but that's okay. It's only 1 every 2 or so that you cannot synthesize and characterize.
Yeah, understood. So sampling in different regions, is that the same as the hypercube sampling that you're talking about? Because I personally did research in Monte Carlo, and the hypercube there you would use in a similar manner as to what you described, or is this another step, the hypercube?
In that one, we didn't use hypercube sampling necessarily, but what we did is we found by chemical similarity what are the most diverse substrates for a Suzuki reaction that we could come up with. They were kind of reasonable molecules. And then the variable that was being optimized in that particular paper was the overall yield over all of them. So individual yields were going up, but we were very interested on is the average yield of all of them. And then we wanted to raise that. Because in screening, you don't sometimes, there's 2 different stages when you do drug discovery, right? One of them is screening or materials discovery, and the other one is process optimization. So in screening, you want the reaction to succeed and get some product. That's enough. Yeah. But in process optimization, then you want to increase the yield of that particular process or molecule that you discovered. And that's a different story. We also have worked on that together with Merck and the University of British Columbia on AI for process optimization. That's another story. But in this particular case, focusing just on the overall yield of the Suzuki allowed us to provide the world a reaction that now anybody can run better in their arbitrary substrate. I mean, statistically, probably will be better to run our reaction conditions than the reaction conditions that were published in 2009.
Yeah. I think also in your work, Bayesian optimization is kind of a workhorse oftentimes. We also use it. Why haven't you moved on to other methods? Just because it works so well, or?
Well, I have a philosophy. I don't know if you have the same, Igmar, but I believe that in machine learning, sometimes somebody loses puts the cart before the horse. Okay, so what I mean by that is, I always like to tell my students and my collaborators on my team, my startups, when you're doing, first of all, let's do a hierarchy. What you're doing machine learning is you want to solve a problem. So first, that's the first thing. So we don't have to forget that. It's kind of funny how people forget that. So many newspapers, it's not clear what problem they're trying to solve, right? They're just developing some random technology. So first of all, at least in my research, there's a problem to be solved, which is I want to design an organic laser. That is the most important thing. And you're going to do anything you can to design the organic laser because that's what you're set to do. It's a science and engineering target. Next, if you go to the next level of what you want to look at, how am I going to get high quality data? That's where the robots are important. Getting data from the literature has been shown time and time by many people. It's very unreliable because your lab is different than my lab and somebody else's lab and so on. Perhaps in your field, biology, is a little bit different because an enzyme is an enzyme. And, but even then, it's garbage, right? People do an enzyme and it's a solvent or the cell is different or whatever. And the biological data is also very noisy. So good data, and therefore robots are fantastic. Eat your own dog food, come up with your own data. Number 3, representation. You mentioned I'm interested in molecular representations. You said I work on fingerprints, and let me correct it a little bit. We developed something called selfies, which is a new representation for molecules that supersedes smiles. As far as we know, it's better than smiles in pretty much all machine learning tasks. So there's a couple exceptions, but I think if you want to use machine learning with strings, you should use smiles. Selfies and not smiles. So I believe representation is next. So you have to think about, okay, am I going to represent my molecules as one hot encoding of linkers? Maybe that's enough. I'm going to represent them as a string or a graph. I'm going to represent them as a 3-dimensional molecule, blah, blah, blah. Finally, the method. That's what most of my students want to be on. Most of my students want to say, I want to do the next diffusion model. I want to do the next ChatGPT, LLM with augmented memory and blah, blah, blah. And, because some people think that's the most exciting. To me, that's the least exciting. So if you follow the hierarchy of importance, once you get to the machine learning model after you picked up the representation, then depends, right? So if you're in screening mode, right, a variational autoencoder, a generative adversarial network, a genetic algorithm. Actually, my lab likes a lot genetic algorithms. We use one that we developed called Janus a lot. Sometimes Janus outperforms any VAE or any other one of those things. So that's another thing that people underestimate, how powerful good generative models augmented by deep learning can be. Evolutionary strategies can be. So we use any of them. Depending on the problem, we will pick the one that we like, and it doesn't matter to us. But that's in screening mode, like in generative model mode. But unfortunately, there is a big disconnect still, right? How to do optimization over feasible sets, right? And there are based on tools like Griffin, Golem, Phoenix, Chimera. We just released one. It's going to come out in the archive very soon, called Anubis. All our different kind of base-up tools for chemistry play a role. Because usually in chemistry, what's happening? You have 500 data points, 1,000 data points. You're trying to optimize a particular process. So there, I think a base-opt, even a Gaussian process-based base-opt might be enough for what you want to do. I think those base-opts, the challenge is that all the extra tools that we are using, like scalarization, non-constraints, we have a paper on non-constraints, non-constraints, delta learning, which is low quality data and high quality data linked to each other, etc., 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 are the sauce, right? It's like if you buy a big piece of chicken breast, that's the caution process. It's not tasty. But if you want to make tasty, you're a Mexican like me, you want to make it tasty, you want to put salsa, you want to put tomato, garlic, right? And those are the different things that make the Bayesian optimizer actually work, right? All the different dressings.
Yeah.
So that's how I think about it. But to be honest, depends on the tool, depends on the problem, the tool that we're going to be using. And I'm pretty agnostic and very respectful of everybody else's tools. And we should use everybody else's tools. And last thing I would say, kind of, I'm going into a rant here, but I also encourage the young scientists and, of course, people like in startups like you to remember that the world is not an Ellipse table with bold. And what I mean by that is sometimes an 87% efficient model is enough, and you can move on to apply it.
Absolutely.
So machine learning, as you know, people keep going, and they want to get a model with 92% and 82%. And my recall is better than your recall, and so on. Ridiculous, right? Because once you cross the bar of utility, better use it, right? In my opinion. So that's what my lab does, and we're pretty happy about that. And I like to talk about it when I'm in podcasts or in giving talks, just for the young people to kind of think about, or old people too, whatever. We learn from each other. I'm not trying to be ageist, but whoever, to think about what's important. It's a very simple reminder. I know I'm saying basic things here. Yeah.
Yeah, absolutely. That's what we've seen a lot. People ask, well, is this algorithm the best, or is this algorithm the best? And I'm like, well, everything is better than what you're currently doing in your lab without a computer. So why do you care, really? It's kind of a way to push action into the future sometimes for some people, to just think theoretically about, well, what would be the best? So because while I think about it, I don't have to actually implement it.
Yeah, we have to get our hands dirty. So like, if as a community we want our hands dirty. So Ingmar, you told me you are a machine learning scientist that is now doing protein design and enzyme design. You're getting your hands dirty, so you know that the world is it. Biological world is a complex and difficult world, and the probably as well that how machine learning is a tool in the toolkit. So I'm very proud of one of my students. His name is Daniel Flam. He's just coming back probably from one of his postdoc interviews. He's interviewing in biology lab, or he came from full pure computer science. So learning what is a molecule, and then he got interested in proteins and antibody drug conjugates, and he's now very interested in gene editing. I like that career path because some people in the sciences are going to the computer science, but we need both. We need also the computer scientists coming back to the science, and like when we meet in the middle, there is this beautiful playground that we all can have fun.
Absolutely. And as you say, it teaches you how other things than you thought up to now are important to have an effect on the real world, actually. Maybe can you tell me a bit about what got you interested in this whole field at all? Like, was it you were always a science buff and it was all just natural, or did you come from somewhere else?
Well, depends what era of my life you're talking about. But first, how I entered into science. When I was a kid, I was asking too many questions to my father. My father was driving around, and apparently there was a sale on an encyclopedia. So he gave me an encyclopedia when I was 6, and that was my present. And I didn't know what to do when you were 6, so I actually read the entire encyclopedia twice. And then through that, I was very interested in history, a bunch of random things. But science stood up. And when I was in high school, I went to the International Chemistry Olympiad representing Mexico. And the International Chemistry Olympiad is this competition, it's global. And when I was there in Norway, turning 18, representing my country, I said, oh yes, I can make it happen. So then I did my PhD at UC Berkeley. My postdoc at UC Berkeley. Was very lucky to publish a paper on quantum computing for chemistry at the beginning of the field. So it was a science paper that got me my faculty job. Then in my faculty job, I started doing quantum computing for chemistry. But also, this is what is relevant, just before my faculty, I was trying to figure out what to write about, and I went to a talk by Sir David King, which was the scientific advisor to Tony Blair. And Sir David King was talking about climate change and what was going to happen to the island of Britain as the climate change water rising happened. Which, I mean, 20 years later, where we are right now, there's floods everywhere, and people are really worried about Florida as it's an existential threat to places like Florida. So that made me think a lot about how to make molecular design faster. And the quantum computing for molecular design obviously was a very futuristic play, but then in the short-term play, I built something called, at the time I was at Harvard. I was at Harvard until 2016, then Trump was elected, and then I left to Canada. I didn't want to stay in the United States, and I love where I am. In University of Toronto is my home. I love it. I'll never leave this place. It's awesome. But when I was there, I built something called the Harvard Clean Energy Project, which was screensavers around the world. I was very inspired by folding at home. You might have heard about those things. Screensavers that do calculations. So we ran 3 million density functional theory calculations with screensavers around the world. People were downloading it and running it. And it was kind of the most unsuccessful project in my life in some sense. Successful but unsuccessful, because I predicted 3 million molecules and almost none were made. A few were made back in Mexico with my collaborators, but that's it. Because I never thought about synthesizability. So that made me change my way of thinking and started working on flow batteries, other projects. And that's around the time that machine learning came out, and I used it. We were fascinated by things like the autoencoder. So we wrote the first autoencoder paper for chemistry. It's now one of my most cited papers. It was published back in 2018. It has probably 3,000 citations or even more. I don't know how much. But that paper was one of the first papers where actually people were doing molecular design with quantum computers. Sorry, with classical computers, right? And now all pharma and everybody is using generative models and things like that for chemistry. But I was very early on, very lucky to work with Ryan Adams and David Dubenot and others at Harvard, building these tools that now are used by many people, and of course extended and multiplied. But by no means we're the only ones that do this kind of thing, obviously. And we were not exactly the first. There were other people that were doing things as early as the 90s. There were a lot of papers on neural networks for molecules by the group of Parinello and others by the 90s. And I even met a chemical engineer showing me papers using neural networks for chemical engineering in the 80s. The first self-driving lab was published in 1978. So by no means you can say you are the first. There's always people before you.
Yeah. I remember in Bayesian analysis, when I did my PhD in it, to think up this, that, and the other generative model and generalization of what's currently published. And then you find a paper from the 70s, which kind of already includes some of the ideas that you are thinking about. So yes, you always build on people that seem so smart, but then they don't spell it out, right? So a lot of what we do today is spelling out something that somebody else has started. Would you say, so you talked about being inspired by this speech by the science advisor of Tony Blair's. Would you say that you have a certain aim of what you want to catalyze with your research? Like, is it climate change, for instance, or drug discovery? Because what's driving you in this direction? You're already nodding, so it seems that is the case.
No, of course, yeah. I mean, it's funny, right? What drives every person, and we're all different. But I think we scientists share a lot of things with each other. But in what I personally am driven for is the slow pace of science and technology discovery. If you look at how long it took for the lithium battery to be commercialized, the lasers in your DVDs and CD recorders, the solar cell, all of them took 25 years from the initial scientific discovery to the early commercialization. And then you have the economic learning curve of another decade or two. Typical example with solar cells, right? Now, I was just on the way back in the train. I was doing something this morning, did exercise. I came back to my house to do this podcast. And I was reading in the train about the solar cells and how there's a company called First Solar in the United States, pretty much the only manufacturer of solar cells in the US. Kind of interesting. And I was reading about solar cell technology, which is what I originally started thinking about with organic solar cells. And it's fascinating how that technology has matured over decades, right? So that really impresses me, because imagine I come up with a new molecular technology. How can I use it? So good example is biotechnology, right? I mean, the COVID vaccine was discovered, I think, in 2.5 days in Moderna. The rest was scale up, right?
Yeah,
I mean, of course, testing and scale up. So we need to get that in materials and molecules, and that's the meta. Now, you alluded to some applications like climate change. Yes, my lab is a little bit agnostic in the sense that organic laser is more of a commercial application. It's kind of an interesting scientific problem. So sometimes I build a tool but apply it to a scientific problem or engineering problem. But yeah, I have an effort in my lab. New papers are going to come out really soon on flow batteries, large scale energy storage. So that's for climate change. And also, yes, as you mentioned, thanks to a great collaboration with my colleagues at In Silico Medicine, I started working on drug design. So I've been lucky to collaborate and know Alexia Voronkov from In Silico, and we have published some papers there. And we're about to post the paper. This is kind of like the preview. I think next week. I mean, the last co-author has it on our 5-year task. I can't believe it's 5 years or maybe 4 years since COVID came out. We were able to come up with a small molecule that binds NSP16, which is a piece of the transcription. Basically the protein. Basically, NSP16 is part of the engine. I'm forgetting right now the language, but part of the protein building apparatus of the COVID virus. So instead of attacking the coronavirus spike, we're attacking actually the NSP16 molecule. Protein, and that was done kind of in my lab with a few collaborators around the world, Masoud Bedadi, also the University of Toronto, and others. The group of Vince Walls, the molecular dynamics calculations. But this was a grassroots effort led by my undergrad at the time, Akshat, which is now a grad student at Stanford. And 4 years later, now we have a drug for COVID. Now, of course, it's a lead candidate. People have to develop it, test it in animals, blah, blah, blah. It will take years. Maybe it will never be done. But this is the power of these kinds of things, right? So what motivated me there is when COVID was going on, I said, we have to do something. And even if it's humble, like with Akshat, undergrad and a few people, we got a donation from a donor at the University of Toronto that we use the money for this. Well, guess what? Now, a little bit later, boom, we have a COVID therapeutic out there, right? So let's see if it's developed. But that's quite kind of like the kind of things that motivate me is having these adventures, right?
Yeah. You build a platform that can do many things and can have many applications, be it in drug discovery or be it in other designs of materials or molecules, whatever they might be, and just pulling, like, I don't know, increasing the length of the lever by machine learning, right? So you can more quickly move things.
Yes, I would say that's exactly what... this is the time to talk about it. I guess the people in communications of my consortium will not be happy if I don't mention it in a podcast. But just in April, it was announced that the Canadian government gave the University of Toronto the largest grant ever awarded in a Canadian context for a university. $200 million Canadian, $150 million USD, to build self-driving laboratories in different applications, all the way from metals and oxides to organoids, an organ on a chip, going through small molecules, going through molecular materials, going through polymers. This is obviously not just me. This is a big conglomerate of professors in the University of Toronto and globally. But it is our mission to do exactly that. I like your analogy to build the levers so that us and other scientists can actually turbocharge the discovery of molecules and materials.
Yeah. Okay. And maybe in order to wrap up, maybe can you give some advice to people that start out in the field of machine learning and chemistry, what they should focus on, how they should approach their work?
Depends what exactly the stage of the career is, but one of the things that I really like, and I think the best students sometimes come out this way, is I tell them, build your own tool, right? So like some of the kids that are amazing is this high school kid that by themselves, they rewrote the graph convolutional neural network or something like that, right? So even if their tool is not perfect, they learn by putting it together. And that learning expertise at the beginning, when they write the first line of code, right, it's very important. Even me, when I had my first sabbatical, which I stayed in Boston, I didn't do anything, but I basically just stayed there. I didn't travel to another university. At the time, my colleague David Duvenol and Dougal McLaurin and Ryan Adams had coded AutoGrad. And I was like, let me play with this. Which is, of course, AutoGrad evolved into, in some sense, JAX now. Right? So, but at the time I was typing and I was like, how did this derivative happen? So I got myself into this kind of loop of automatic differentiation and so on. And now, funny, just yesterday, and then I wrote a paper on automatic differentiation for quantum chemistry with my student Teresa Tamayo, which is now a little field, automatic differentiation for quantum chemistry. But at the time, it was like, wow, this is going to be a very important tool for science. Forget about the neural networks. For science, automatic differentiation is going to be important. I was behaving a little bit like an undergrad. Just by coding one single line of code, my brain exploded. And I don't have time to code. I mean, that was the only time I had a little bit of time to code. My next sabbatical is next year. I hope to sit down and code something. So yesterday, I was sitting with my friend, my new student, but also friend. I love him. His name is Manuel Druchald. Just started his PhD in my lab. He's from Germany. I guess, Ingmar, you're also from Germany. So Manuel works on a tool called Enzyme, which is a compiled differentiator. So Manuel and I were talking about the cool things, and I'm not going to disclose the ones that we're doing, but the cool things that we're going to use with Enzyme, his masters. And Manuel's enthusiasm yesterday in my office makes me remember what good students in this field are, like Manuel and others in my lab. A recommendation is just be passionate about what you're doing. Don't compare yourself to others, which many people do. They look at somebody from MIT and how many papers they have or something, or whatever. One of my students was telling me, oh my God, it's just like, look at this MIT grad student. He's my same age, but he has 3 NeurIPS. And I'm like, that's he, and you're you, right?
Yeah.
You're going to have your own papers. So just do your stuff, have fun. Actually, that's another important thing. Have fun. And as a young guy, don't worry too much, or gal, don't worry too much about repeating somebody else's work. Just build your own knowledge, and then when you get older, then ask yourself the Whiteside's questions. I think George Whiteside put them the best. My former colleague at Harvard, which is a fantastic scientist, and George Whiteside says it a little bit like this. And I guess this is my version of George Whiteside. I think he says it a little bit different, but my version, what I say in my lab is, once you're older enough and you can pull this off, is, has somebody else done it before? If the answer is no, then that's a good thing to do. Second, is it remotely possible? If the answer is yes, that's where you want to be. You want to be at the edge of imagination. And finally, will people care about? You and I have been talking most of this podcast on that question. So if those are the 3 requirements, then that's a good paper to work on. So if you're a young person and you're thinking about, what should I work on? Follow this kind of mantra, and I think you will come up with something new for the world. And it will make you happy, even if it's a small contribution, even if it's a simple something. I'll tell you one last lesson. I have a fantastic student. His name is Naruki Yoshikawa. I just say Naruki. That's exactly one of those amazing students. Naruki is working on things that sound simple, but they are not. We're trying to build this robot that does chemistry, but unlike traditional robotic chemistry, it has eyes, picks up things, drinks from them, plans. So robots that are more like human-like, they actually plan and execute and listen to language, and they're doing chemistry. So that's a more longer-term project that my lab has, I haven't even mentioned, in collaboration with Animesh Garg and Florian Scruti, which are actually the real roboticists, the ones that really push this. Okay, because I am the chemist. I know at least here. But anyway, we have papers with Naruki on a digital pipette, right? So that sounds like... I told Naruki, right? This is like a very important contribution. We have a $200 pipette. that we're going to be using for this. Let's do a paper on it. Let's just publish it. And it's interesting the things that the reviewers make also. Repeat pipetting 200 times, so my poor robot was there pipetting and stuff. But what matters about this is that's a contribution on itself and looks small in some eyes of somebody, but to us it's huge because it builds around the pipeline of our robot that is going to be doing chemistry kind of in a more unsupervised fashion, in a more chaotic environment. Like if you were to see my desk right now, I guess we're in the camera, right? So people can see my desk is a mess. Okay, so look at that. So it looks my library looks very organized, but so the robot has to be able to operate in a mess like that. So I don't know. Those are the things that keep me up at night. I just tell everybody entering the field, no matter what your age is. I say young. What I mean by that is young in terms of spirit, and just you're starting in the field.
Yeah.
Just have fun and follow some of those things, and I think you will be interviewed by Ingmar in his podcast in the next year.
Yes, I will. Thank you, Alan, for being on Machines and Molecules. It was a very entertaining talk, and I hope to see you in Toronto or over in Berlin.
You come, visit, and I like that. Ingmar, we have a tequila shot in Berlin or a tequila shot in Toronto. I really appreciate things like people that do what you're doing, Ingmar. Sometimes it takes a while to be scheduled for a podcast. And my schedule is a mess. But the reason I accept them is because I really like people that are trying to disseminate science. So what you're doing, Ingmar, is very important for the field. So thank you. You bring things, popularize them, make people aware of them. And therefore, thank you for doing this, which I know is a lot of work. So thank you, Ingmar. I really appreciate it.
Thank you, Alan. And see you for a tequila shot.
Tequila shots. Deal.